Good day, everyone. I am Mark Henry Sokyat, a computer engineering student from the Philippines, and today I will present our study entitled Fitness Assessment of Philippine Bills using YOLO V8. Here are the brilliant minds behind this study. Yours truly, Mark Henry Sokyat, my co-author and also a student from the Philippines, Amir Allen C. Abinuman, together with our advisor and professor, Noel B. Linsangan. So in the Philippines, fitness standards for paper currency have long been established and clearly defined. However, despite these standards, many damaged bills continue to circulate, reducing their value and reliability in our monetary ecosystem. When we think of research on currency, the focus is often on counterfeit detection, an issue that remains highly relevant, yet one critical aspect that is often overlooked is the fitness of paper currency, or the physical condition of bills that remain in circulation. This brings us to the identified research gap. While there is substantial work on counterfeit detection, there is limited research dedicated to classifying and evaluating the unfit characteristics of Philippine banknotes. This study seeks to address the problem of unfit currency circulation by developing a working prototype for efficient bill classification. The core objective is to design a system that can automatically distinguish fit from unfit Philippine banknotes using Jetson Nano and YOLO V8. Specifically, the study will develop a prototype equipped with a Raspberry Pi camera to capture images of both fit and unfit bills, apply YOLO V8 to extract features and classify the condition of the banknotes, evaluate the model's accuracy and performance in determining bills fitness. Ultimately, this research aims to provide a practical tool that enables faster and more reliable classification of Philippine currency, supporting the Central Bank of the Philippines in enforcing its currency fitness guide and ensuring a healthier flow of money in circulation. For the next slide, we now take a look on the conceptual framework of the study. We will use images of fit and unfit paper bills as an input in the system, which will then be fed to the model trained to classify whether the bills contains unfit characteristics. In the case that unfit characteristics are present, the system will classify the input as an unfit bill. On the contrary, on absence of unfit characteristics, the system will classify it as a fit Philippine bill. Shown in the presentation is the hardware development for this study. We use Jetson Nano as the main computing hardware for the system, together with Raspberry Pi camera as the main input component and an LCD display as the main output component. Shown in the presentation is the software development setup and configuration applied in the system's training, validating, and testing phases. Training the mo- Training the model is done on a personal computer before transferring the model to Jetson Nano for testing. Listed are the specifications of the personal computer, an operating system of Windows 11, an NVIDIA RTX 3050 GPU with 16 gigabytes of RAM, and an Intel Core i5 13450HX CPU processor. This method is done to achieve a faster training time due to the computing constraints of Jetson Nano and a relatively large dataset. Additionally, parameters are set to accommodate the training iterations. 200 epochs with a 640 by 640 pixel image size are fed to the YOLO V8 and that PT pre-trained model to ensure a stable model convergence and to achieve the best possible result for the training process. Overall, these configurations and specifications ensure the fitness assessment system's compatibility, reliability, and efficiency. Next is the software process for the system's graphical user interface. Once the capture button is pressed, the system will then capture an image of the bill that is on the platform. The image will then be fed to the trained model, classifying whether it is an fit or fit bill. The prototype is designed to capture clear and detailed images of Philippine banknotes for classifications. The experimental setup for this study, a sample bill is placed on a designated platform positioned directly beneath a Raspberry Pi camera mounted at the top of the enclosure. The camera angled downward at a fixed distance of 11 inches, ensuring a consistent image framing and accuracy. To enhance visibility, two light sources are installed on opposite sides of the camera directed toward the platform. This controlled lighting setup provides balanced illumination, reducing shadows and ensuring that the camera captures high contrast images with precise details, essential for accurate classification. So the figure in the screen depicts different training, validation, precision, recall, and mean average precision graphs. The first row from the left is the training losses, which present a consistent downward trend, suggesting that the model is learning effectively within the training process. In total, 1,327 images of Philippine bills with unfit characteristics were captured, and additional 200 images of fit bills. Sum up the novel dataset for this study. A total of 6,841 annotations were extracted from the images, which were then split into training, validation, and testing sets. There are seven classes. On average, there are 760 annotations per category. Using RoboFlow's pre-processing and data augmentation, 3,663 images are generated for training, validating, and testing. Like the training losses, the validation losses present a downward trend, implying that the model is not overfitting. However, there are sudden spikes in the graphs at the early stage of training, suggesting that the model is still adjusting from the initial training phase. Lastly, the mean average precision depicts a strong upward trend, indicating the model's precision improves significantly over time. Next, the table in the presentation summarizes results for assessing Philippine bill fitness, classifying bills as either fit or unfit for circulation. Out of 60 samples, 12 were correctly identified as fit and 35 were correctly identified as unfit. However, 4 genuinely fit bills were incorrectly predicted as unfit, and 9 genuinely unfit bills were misclassified as fit. The overall effectiveness of the classification model for the system is calculated using the provided accuracy formula. Accuracy is determined by the ratio of the total correct predictions to the total number of instances. The system made 47 correct predictions out of 60 samples, yielding an accuracy score of 78.33%, which indicates that it correctly classified nearly 4 out of 5 Philippine bills tested for fitness. Here is the sample output for our system. As you can see, an unfit paper bill is captured. The output displays the bounding box of marked unfit characteristics, followed by a vertex at the bottom of the screen, whether the bill is fit or not. In this case, the bill is unfit due to charring and decay. In conclusion, the system's performance is measured by its accuracy, resulting in 78.33% after it made 47 out of 60 correct predictions. During testing, future work will implement a sensor capable of higher capture resolution, preferably a minimum of 1080p resolution, and a computing hardware with a high performance GPU matched with expanding the dataset, implementing instance segmentation, and other future functionalities. That is all. Thank you everyone for listening. I will now entertain questions regarding our study.